Welcome to the new era of video creation with BeoZ8. Today, we will discuss how do you approach debugging and improving the performance of a deep learning model that is underperforming in production. Before jumping into debugging, it's crucial to define what underperformance means for the given system. Is the issue accuracy degradation, slow inference times, or unexpected outputs? The first step is analyzing production logs. These provide insights into error patterns, failure points, and distribution shifts. Tools like Prometheus, ELK Stack, and TensorBoard help track runtime behaviors. Additionally, user feedback and real-world edge cases often reveal problems that weren't present in the training data. Comparing current model behavior against its expected performance helps identify what changed and why. Many performance issues stem from data-related problems rather than model architecture. A common issue is data drift, where production data distribution shifts away from training data. Feature engineering errors, such as incorrect normalization, categorical encoding mismatches, or dropped features, can degrade model performance. Another key area to inspect is labeling inconsistencies. If the dataset contains misannotated samples, the model may be learning incorrect patterns. Lastly, check for missing or corrupt data. Incomplete datasets may introduce biases or missing feature values, reducing model reliability. A deep learning model can underperform due to overfitting or underfitting. If a model achieves high training accuracy but poor validation test accuracy, it is overfitting, learning noise instead of generalizable patterns. If both training and validation accuracies are low, the model is underfitting. It lacks capacity or is not optimized effectively. To diagnose, inspect learning curves, loss versus epoch graphs. If the training loss continues decreasing while validation loss increases, the model is memorizing rather than generalizing. Regularization techniques like dropout, L1, L2 penalties, and data augmentation help combat overfitting, while increasing model complexity, e.g., deeper networks, better architectures, can address underfitting. Hyperparameter tuning plays a significant role in improving model performance. Learning rate tuning is critical. A high learning rate can cause instability and poor convergence, while a low one can slow down learning. Batch size trade-offs exist. Larger batches improve computational efficiency but may lead to worse generalization. Optimizer choice impacts convergence. SGD provides stability. Adam adapts better to noisy gradients, and RMS prop is effective for recurrent models. Architecture fine-tuning, adjusting layer depth, neurons per layer, or activation functions helps refine model capacity and efficiency. If the problem is slow inference speed or high computational cost, model compression techniques help. Pruning removes unnecessary parameters, reducing model size without major accuracy loss. Quantization converts floating point values to lower precision, e.g. FP16, INT8, to improve execution speed. Knowledge distillation transfers information from a large teacher model to a smaller student model. Hardware-aware optimization involves adjusting architectures to exploit GPU, TPU optimizations efficiently. AI models often exhibit biases due to imbalanced training data, biased annotations, or structural model limitations. One way to detect bias is to evaluate performance across different demographic groups. For example, does a facial recognition model perform worse for certain skin tones? Explainability tools like Shapley additive explanations, LIME, local interpretable model agnostic explanations, and Captum for PyTorch help analyze model decisions. These techniques highlight feature importance and reveal biased decision-making. Bias can be mitigated during training by modifying loss functions to encourage fair predictions or using adversarial debiasing to enforce fairness constraints. Post-training corrections, such as reweighting data samples or applying fairness constraints during inference, can also help. Ultimately, addressing bias requires a combination of data balancing, explainability, and fairness-aware optimization techniques to ensure that models generalize fairly across diverse populations. One major challenge in debugging deep learning models is identifying and handling edge cases, examples where the model fails unexpectedly. To tackle this, error analysis is crucial. Engineers should analyze misclassified samples to find patterns in failure cases. For example, a self-driving car vision model might fail in extreme weather conditions due to insufficient training data for those scenarios. Another technique is adversarial testing, where small perturbations, such as modifying a few pixels in an image, cause the model to produce incorrect outputs. This reveals vulnerabilities that can be hardened against adversarial attacks. Models also benefit from training on hard examples, cases where the model struggles. Active learning can help by prioritizing uncertain predictions for human annotation and retraining. Counterfactual analysis tests how small changes in input affect output. For example, does changing a single word in a chatbot prompt drastically alter the response? If so, it signals unstable decision boundaries that need refinement. Debugging edge cases ensures robustness, reliability, and trustworthiness in real-world deployments. AI models don't stay effective forever. Data distributions change over time, causing performance degradation. Continuous monitoring and retraining are critical to maintaining high accuracy in production. Performance monitoring tools, e.g., Prometheus, Grafana, Seldon, MLflow, track changes in input distributions, accuracy, and response times. Drift detection algorithms compare current data with past distributions to identify when a model is no longer valid. Automating model retraining helps mitigate performance degradation. Pipelines using MLOps frameworks, e.g., Kubeflow, TFX, Airflow, enable efficient retraining and deployment without manual intervention. A/B testing is essential before fully replacing an existing model. Engineers deploy two versions, A and B, and compare real-world performance before committing to the new model. Finally, active learning allows models to improve dynamically. When encountering high uncertainty cases, the model can flag them for human labeling and incorporate them into future training cycles. Without monitoring and periodic retraining, even the best AI models can degrade quickly in production environments. As AI systems scale, debugging becomes more complex. Engineers must develop automated debugging pipelines that continuously detect and correct errors without manual intervention. Self-healing models use adaptive learning to automatically adjust to data shifts. These models detect when accuracy drops and trigger self-retraining mechanisms to adapt to new conditions. Federated learning allows models to train across multiple distributed locations without sharing raw data. This is especially useful for privacy-sensitive industries, e.g., healthcare, finance, where centralized data collection is not feasible. Meta-learning, or learning to learn, helps models generalize better across unseen tasks by training on a variety of different distributions. This approach is critical for models that need to adapt quickly to new environments with minimal labeled data. By integrating automated debugging, adaptive learning, and advanced training strategies, AI engineers can build scalable, resilient systems that continuously evolve in dynamic environments. Debugging deep learning models is a multi-step process that involves identifying the source of underperformance, whether it's data drift, hyperparameter tuning, or architectural flaws, optimizing model efficiency using pruning, quantization, and distillation for deployment, mitigating biases by analyzing performance across demographics and employing fairness-aware techniques, ensuring robustness through adversarial testing, retraining on hard examples, and active learning, monitoring models in production using observability tools, retraining pipelines, and adaptive learning approaches. AI models are never truly finished. They require constant evaluation and refinement to stay relevant. A structured debugging and improvement process ensures that AI systems remain accurate, efficient, and fair in real-world deployments.